Today we discuss some aspects related to the implementation strategies for digital design. And here the main issue is the fact that in the last 40 years, what we have observed is this increase of chip complexity that is faster than the increase of design productivity. What does this mean in particular? It means this specific thing. Of course, we are able to design more and more complex integrated circuits, and we have more powerful tools available in order to design those circuits. But what is happening is that the increase in the complexity of the circuits is faster than the increase in productivity. Just to put some numbers, Okay. Sorry. Just to put some numbers, if you consider from 1980 up to now, the average increase in the complexity of a chip, simply counted as the numbers of transistors per chip, is something close to 58% per year. So each year, the number of transistors you need to put on a chip increases by, on average, 58%. The number of the productivity growth counted as the number of transistors that any given person can put on a design in a month is increasing of only 21%. And the second thing is, the second number is mainly due only to the fact that that as a designer, one can use more powerful tools, typically also tools that work at a higher level of abstraction, so that every tool can help to put on a circuit more transistors. But you can see that there is a significant difference in the growth rate, and this translates in a practical thing, is that the size of a team which has to design a complete integrated circuit is increasing, has to increase, because the difference between the two numbers means the average number of the average increase of the size of the team to design a chip. It's something close to 40%, and this is the reason why now for a complex integrated circuit we easily have a number of designers of the order of 1,000. Okay? If you just compare with the simple bit of information that I give you at the beginning, the design of the first Intel microprocessor was done by just 3 persons, 3 designers. Of course, now a modern microprocessor by Intel is well above a few thousand designers. Okay? And so this brings 2 issues. One, of course, is to understand how can we obtain this increase in the productivity, and how we can maximize this increase in productivity. And on the other hand, of course, we need to have tools that allow many more people to work on the same design. This is an implication of Moore's law, basically, because, of course, if you have the possibility to double the number of transistors per chip every 1 to 2 years, of course, you also need to be able to design those integrated circuits of increasingly larger size. So, what are we going to do today is to look at how in the history and at present the productivity of design has been increased. And as you will see, the most important factor in this increase has been the possibility to move to a higher layer of abstraction in the design, which is, I mean, more or less what has been happening also in software design. Okay, that's a significant move to a higher level of abstraction. So, this is made possible by the introduction of new design technologies. What you can see here in the slide is a list of different technologies that have been introduced in the market for digital design since the 70s until basically the last decade. And actually, the first in line are the so-called programmable logic arrays that are also called PLA, that some of you have already seen in the basic course in electronics. So that I will not touch in particular in this discussion. Then we have standard cells, which are digital cells for typical logic gates or typical digital functions that are already ready, and then you have to directly take and place in your design instead of, let's say, building the functions transistor by transistor. Then we have macro cells and module compilers, which are even larger digital blocks ready for use, and then gate arrays and reconfigurable hardware. Now, in the following, I will go through each of these items in the list in order to, let's say, discuss a bit what is their function, what they are consisting, and so on. Okay, for the moment we take this list and let's put it aside for a minute in order to consider the structure of a complex digital integrated circuit. For example, a microprocessor, to take let's say the typical example. So in microprocessors there are a few different blocks from a functional point of view that are represented here. Of course, we have a control block which manages the operations of the microprocessors. There's a memory block, on top a data path, and a block dedicated to interconnections and input-output, which means communication to the external world. The control block basically controls the operation of the microprocessors. The memory block is let's say, self-evident. In the memory block, we can think as if there are all the different types of memory required for microprocessors. The data path is the part of the microprocessors where the logic operations take place. So, for example, in the data path we have the ALU and the different types of let's say, circuits. So circuits for operations on data. So that is the reason why it's called data path. So just to read the diagram, the blue links indicate the the control information that is coming from the control block to the memory, to the interconnects, and to the data path. So those connections, let's say, serve the purpose of controlling what is happening in the other blocks, and the red interconnections represent the data flow. So data, for example, go from the data path to memory and the other way around, or from the memory to the external world and the other way around, or from the data path to the external worlds through the interconnect and I/O block. Okay, so this is a very simple structuring of what's happening in a microprocessor, and I do it for the purpose of discussing the different type of digital circuits that we have in the different types of block. For example, in the data path, there are, as I mentioned, the arithmetic operations and the combinatorial functions. And this means that typically the data path is made of custom cells. So of cells, of functional blocks that are specifically designed for the functions they have to perform in that block. Okay, so they are typically designed transistor by transistor or small gate by gate. So transistor by transistor or gate by gate, depending on what is the design methodology that we use. The control part is essentially a finite state machine controlling the operation of the microprocessors, and it basically it's composed basically by standard cells. So as I mentioned before, standard cells are typically simple logic gates. And simple logic gates or relatively simple registers, let's say simple blocks, as the name implies. The memory part instead contains different types of memories. Of course, we have read and write memories, read-only memories. We can have single port access memories and double port access memories, and all the different types of memories. And in this case, of course, you typically need to have a memory bank, so a relatively large block of the size that is needed for the microprocessors. And so typically the memory consists of so-called macro cells. Macro cells are, let's say, standard blocks that are relatively large, that can be, let's say, directly allocated on the chip. And finally, the interconnect block consists of specific microcells for input-output interfaces. So they have to be specific for input-output interfaces because in order to, let's say, communicate with the external world, one has to have, let's say, significant current drive capability or different levels of voltages and so on. So we typically have to use specific macro cells, specific in the sense of specific for the input-output block to use in that part. So each of the things that are specified between parentheses are associated to a different type of design. So we have basically 3 different types of designs have been indicated: custom cells, standard cells, and macro cells. Okay. Let me just, okay. So, just to summarize this aspect, custom cells are logic cells, so small logic circuits, let's say coupled together, that are designed transistor by transistor, one transistor at a time. So this means, from the point of view of design productivity, slow, okay, because you have to place in the circuit each transistor individually, choose them, and let's say also design them in the sense of choosing a width and the length for the transistor channel. Then standard cells are typically logic gates, but not only logic gates, also sometimes registers that are already designed and then that I can use as, let's say, elementary block. For example, I need a NAND, a 2-input NAND, and then I can take one and use it directly in the circuit when and where I need it. And of course, in this specific situation, with standard cells, I can go faster because, of course, instead of placing and designing and choosing one transistor at a time, I can work with one logic gate at a time. And the macro cells are larger cells. For example, I can allocate a 64 megabit static RAM as one single macro cell. And of course, in that case, I can be extremely fast because I'm working with large blocks. Okay. So, of course, this is one part, how I choose the single blocks and the single gates that I need for the digital circuit. The other problem is to interconnect those blocks and then to allocate them, because in the end I need to have a layout of the whole circuit. And then, of course, things change because this, the allocation of the various blocks is called placement. Placement in a 2D area of the different blocks, and the interconnection between the different blocks is called routing in let's say, digital design terms. And so, of course, in terms of design productivity, if the placement and the routing is manual, semi-automatic, or automatic, it changes a lot. And also from that point of view, there are tools that can do at least a semi-automatic placement and routing of the different blocks. And of course, the possibility to use those tools depend on the regularity of the design. For example, for the data path, since I have different logic functions, often ad hoc logic functions that I have to implement, also the placement and routing has to be done, let's say, manually, because the structure is again an ad hoc structure, which is not easy to automatize. On the other hand, for example, the memory has a very regular structure, and also the placement and the routing of the memory can be done automatically. The control block is somewhat in the middle, because it's a finite state machine, so it has a, let's say, standard architecture. It's much more regular than the data path block, but still not, let's say, as regular as a memory. And also the other very regular structure is the block dedicated to input-output, because more or less in all the integrated circuits you have the same interconnect and input-output block depending on the number of digital input and outputs that you have. Of course, the more regular the structure is, the easier it is to use semi-automatic placement and wrapping tools, and the faster I can go with the design. Okay. In addition to the, let's say, placement and routing and interconnection between the different blocks, if we let's say think in terms of signal flow and information flow, we need to take into account that we are talking about an electrical circuit. So in addition to the, let's say, data interconnections, we also need to provide the power supply to all the cells, of course, and also the clock to all the cells. So in terms of the placement and the routing, we also need to consider that in addition to the signals, we need to route the clock to all gates, and especially the power supply. Of course, also that is critical from many point of views, also because the clock distribution is critical because the clock is the fastest signal in a digital circuit, and it needs to be provided to all the logic gates, so you need a very let's say powerful clock driver, and also the clock distribution must be very careful because you want to have the clock in phase in all for all the logic gates, the same phase for all the logic gates. For the power, the situation is a little bit easier from the point of view of speed, because of course power is a DC signal, but I mean, still you need to bring the power to all the logic gates. So that part is significant from the point of view of the attention one needs to dedicate to it. Okay, so what is the result of all of that? Just to have a let's say pictorial view of the situation. This is something that I've already shown you. It's the first microprocessor by Intel. It has been designed by three people. Okay, it was a 10-micron process with a little bit more than 2,000 transistors. Of course, this is something that can be done by hand. So it's custom design. Each transistor is individually put on the circuit. So first one does a schematic, then one, let's say, really layouts each individual transistor on the design. Of course, this is the size. That is actually doable. Three people around the table can discuss and decide what to connect to what to put where. Of course, that is relatively easy. You see, if you look at the image, you can see that the design is not really regular. It's really ad hoc because the interconnections are done where one needs them. Okay, so you have these lines that interconnect the different blocks. The placement is not regular. It's really done in an artisanal way. Okay. Of course, this thing is not really doable when you increase the number of transistors on a chip. If we just consider the first 20 years, no more than that, from the 4004 to the 84, 86, you see the structure becomes larger, and also you start to see much more regular structures. You see, for example, here, these are very regular arrays. Of course, these regular arrays are cells that are placed in a quasi-automatic way. And it's typically the structure that you see. When you have, for example, this part is very likely an SRAM cache, so a memory bank. Once the size of the memory bank in terms of bits is decided, you can just allocate the bank on the chip. And this is a structure that is already ready to be used on every chip design. So, and the trend is very clear when you go to complex and more complex and more complex circuit, you start to see very regular regions, quite large, appearing, that are the large macro cells ready for use. Okay. In the use of macro cells, large blocks ready for use, there are, of course, some advantages, but also some disadvantages. Let's consider them in particular. So, for sure, one can add in flexibility, because the large macro cells can be reused in different designs, of course, and especially some macro cells that are programmable, so macro cells whose functions can be programmed by software, also provide the advantage of providing generic hardware then can be upgraded by changing only the software. So these two are critical advantages that appear when one can use, let's say, macro cells or programmable blocks. But of course, there are also, let's say, disadvantages that in some situations might be significant. And one of these disadvantages is the loss in performance that is really a constant. There is always loss in performance when one uses a macro cell or when one used a block that can be programmed by software. And this loss in performance is due to there's a loss in performance because the programmability, of course, provides an overhead, and somewhat the programmability is also, let's say, requires instruction decoding that, of course, slows down the operation. At the same time, exactly for the same reasons, there is also an increase in energy consumption. Of course, when you have a larger circuit, you can also have, typically larger circuits also have a larger power consumption. We shall look at some specific examples of this situation in a few minutes. And this trade-off is always there. So, and it's quite similar to the trade-off that you have in software when you go to higher level to higher levels of abstraction. You have an increase in flexibility and in reusability, but of course you typically lose in performance. So this trade-off is very frequent. Typically, you have the minimum flexibility and the highest energy efficiency and performance for circuits that are fixed in manufacturing, so that are custom hardwired, that you cannot change after you have, let's say, fabricated them. Then you can increase the flexibility with configurable hardware, which allows you to, let's say, modify by software only some parameters. But this thing, which is quite simple, of course increases the flexibility, but represents a loss in performance and in energy efficiency. Then you can go to a different situation. For example, for some applications, instead of having, let's say, a custom hardware to implement that specific application, you can have an application-specific processor, which can be, for example, a DSP, a digital signal processing processor, or a GPU, graphical processing unit. Of course, those processors are specific for the applications and are totally programmable, but of course they represent a loss in performance and in energy efficiency. And at the other end of the spectrum, you have the embedded processor, the generic embedded processor, which is not even application specific, so a further increase of flexibility, but again a loss of energy efficiency. So this is a pretty clear situation that pretty clear trade-off that you have. Let me stress this aspect. Both when you have to choose between a custom design transistor by transistor and a design done with macro cells or with programmable cells, or when you have to consider a complete solution to implement, let's say, a digital function, and you can choose to implement them with a custom hardware or with a microprocessor on which you run a code dedicated to, let's say, to that specific function. Okay.
Sir.
Yeah.
Other accelerators, for example, are like embedded microprocessors or application-specific processors. For example, accelerator for machine learning or fast food.
Okay. I would put them as configurable hardware, depending on the type of application. It really depends a bit. For example, the TPU. TPU is the so-called tensor processing unit. Is the processor by Google implementing dedicated to machine learning applications, and that is likely an application-specific processor. It's because application-specific processor is a very wide category. It can be more or less specific. Okay, so maybe TPUs are more specific than GPUs in the sense that you can use GPUs, for example, for machine learning, but you cannot use TPUs for graphics. So that is. So they are more specific, but they are still a specific type of application. There are also integrated circuits dedicated to machine learning, let's say the category of hardware accelerators, that have very little flexibility. For example, there are accelerators that implement a neural network in which the only thing that you can change are the weights, but the architecture of the neural network is fixed. And that case is by definition a configurable hardware in which you can only, let's say, configure a few parameters. In that specific example, you can configure only the weights, and then the rest is more or less fixed. So it really depends on the let's say degrees of freedom that one has in the programmability part. Okay. So, but just to reply to your questions, they can be somewhat in the somewhat, or either in the configurable hardware category or in the application-specific processors. Okay. I mean, this is a sort of schematic division, but of course you can in principle have a continuum between the two things. The one thing that I want to stress is that from one category to the other, you really have a factor of one order of magnitude in the change of performance and of energy consumption. It's really huge. So, but by performing an application on a GPU instead of an embedded processor, you can increase performance by one order of magnitude, easily. And by two order of magnitude by going on configurable hardware, and three order of magnitude using a custom hardware solution. So you really have a huge change, and of course you lose a lot of flexibility in the process, because a custom hardware can be used only for one type of application, while of course the processor can be used for many types of applications. But the difference is not small in terms of performance. And this is why you start to see in the last few years specific circuits for machine learning, because there are critical problems in performance that you cannot easily solve with brute force by using larger and larger, let's say, arrays of processors, and but you can significantly do it, for example, on a small system if you have a custom hardware. Okay. At this point, it's useful to make some considerations on the cost of an integrated circuit. And the reason for that is that, of course, from the point of view of performance and energy consumptions that are important parameters, it makes sense to have, let's say, less flexible hardware. So to use a custom hardware instead of a microprocessor, only to consider the two ends of the spectrum. So one can ask, why should people use general microprocessors instead of custom hardware, if custom hardware is much more performing and more energy efficient? And the real reason is cost. And the cost is mainly related to the number of chips that are fabricated of a specific type. So we need to make some quantitative consideration about this aspect. So the cost of an integrated circuit is the sum of two components, the so-called recurring expenses and the fixed expenses. There are no recurring expenses. So the recurring expenses are also called variable costs, and are those costs that are proportional to the sales volume, to the number of chips that you have. But also you have non-recurring expenses, so the so-called fixed costs, that are the costs that are totally independent of the sales volume. For example, the design cost is a fixed cost. You have design cost at the beginning, independently of how many chips you sell. you have the cost for building a fab, which more or less are independent of the number of chips you sell. And then you have the manufacturing costs that are more or less proportional to the number of chips you sell. So these are easy costs. But there are also some additional things. For example, if you remember our discussion, in order to fabricate an integrated circuit, you need to produce a set of masks. Okay? And the cost of producing the set of masks is a fixed cost. You produce them once and then you use for all the chips. And it's not a negligible cost. It's still of the order of something like 10 million euros for a modern microprocessor, for example. So it's a significant cost. And in addition to that, you have you have to consider that you typically fabricate a large wafer at once. And so in a large wafer, you have several integrated circuits, a few hundred integrated circuits. So that is the minimum amount of chips that you need to fabricate, because otherwise you pay for a whole wafer and you don't use all of it. But on let's say in a general way, we can distinguish between the fixed costs and the costs that are proportional to the number of chips that you made. And obviously, once you have those costs, the total cost of one chip is the variable cost of one chip plus the fixed cost divided over all the number of chips. And this is, of course, obvious. But in practice, and this is in practice was what changes everything, because if the application is very small and you can, for a specific hardware, sell very few chips, then the denominator becomes small and the cost for the custom hardware solution, even if the chip is small and it's not really a large and very complex microprocessor, the cost can become, let's say, extremely large. And this is a factor that one has to consider in the choice of a solution. Very often, the use of a programmable solution or of a general purpose microprocessor can be very convenient from the point of view of cost, because even if the processor is very large with respect to what you need to use of it, then in practice the cost can be reduced. The quantities that enter the consideration of the cost of an integrated circuits are pretty are more complex than those, and it's interesting to look a little bit more into the details of it. Because there is also a physical consideration that enters in the costs. So most of these considerations have already done. The fixed cost, the NRE, are the time and person months required for the design, as I mentioned, the design expenses, plus the production equipment dedicated to a specific chip. So the mask set and so on. The recurring costs are the cost of the die. The die is the piece of silicon on which the circuit is fabricated, and the cost of the die is more or less proportional to the area of the chip. That's it. Then you have the cost of die test, because you need to test the chip after fabrication. The cost of packaging is an additional cost. And then the important part is the denominator, which is the cost of the which is the percentage of properly operating chips, what is called the yield. The yield in Italian would be la resa. The final test yield is the percentage of chips that after the test are operating according to specifications. And this percentage is extremely critical because it depends on many parameters. One of these parameters is the maturity of the technology. Because, for example, typically when a new technology is introduced, the yield is quite low, something like, for example, 20%. And it's a realistic number. So you have a new process, 10 nanometer FinFET process by Intel. The process starts. During the first 2 years, you have a yield of 20%, which means that only 1 out of 5 chips are really working. You need to really put the other 4 in the trash. Okay? And then, after a while, after a few years, then the process starts to work nicely. It is tuned, let's say, effectively, and then you start to have a yield of something like 80%, which is a relatively good yield. And of course, you can think that from a yield of 20% to a yield of 80%, it means that the recurring costs go down by a factor of 4. And this is something that is really critical in the adoption of the technology, because of course the costs for the adoption of a new technology are very high at the beginning, just because of the yield, and then become very low when the process is well tuned. In addition to that, there is another factor, which is the factor that the yield depends on the area of the chip. So before I discuss this aspect related to the area, I was forgetting that I had this equation that, let's say, expanded the argument, the variable of the cost of the die in a very easy way, because you see the cost of the die is roughly the cost of a wafer, okay, una fetta, over the number of dies that you can extract by every wafer. And this is let's say the obvious part. Then in addition to that, you have the die yield, which is the percentage of good dies. And this is because you can have problems at the level of dies, exactly because you can, let's say, detect a bad die, a die that you have to put in the trash before testing, because, for example, during the cut, the die broke. Okay, so you can, let's say, put it away, or after the final test. So you typically have 2 different numbers. I mean, this difference is not very, very, very important. It's pretty, let's say, it's very technical, but it's not very important. When you look, if you don't consider for a moment the die yield, you can see that the cost of the die is inversely proportional to the area. It's proportional to the area of the die. So to how large the chip is, because the cost of the wafer, of the fabrication of a wafer, is a constant for a given technology, and then at the denominator you have the number of dies per wafer, which is something that is inversely proportional to the area of the die. Okay, so this cost of the die is something proportional to the area. Okay, the die yield is also depending on the area. In which way and why? Let's discuss first why from a qualitative point of view, and the specific functions let's say can be discussed later. Why is that from a qualitative point of view? The main issue is the following. If you consider how are chips designed now, a single failure in a chip, a single failure, for example, in a logic gate or in a register of a chip, basically makes the whole chip bad. So it means that you need to put in the trash bin the chip. And if you assume that the defect is, let's say, something that can occur in any position of the wafer with the same probability, to make the simplest assumption, then the probability that you have a defect on a chip is proportional to the total area of the chip. So this is the basic assumption. That is almost completely true. It is not totally true because there are some circuits that can compensate for a single error. Let's say that are robust for single errors, but of course they are not robust to two errors in the same circuits and so on. So this is just a simplification of the actual process. But more or less, there is this significant, let's say, consideration that the larger the chip is, the lower the yield is going to be. So that when you look at the cost of the die in terms of recurring expenses, you have two trends in opposite directions, because the larger I was saying something wrong. They are not in the opposite direction. No, they're in the same direction, because the larger, you have two trends to consider. Let me correct. You have two trends to consider when you look at the cost of die. Because the larger the chip is, the smaller is the number of dies per wafer, but also the smaller is the yield. So the cost per chip is increasing significantly for two reasons. The, let's say, detailed dependence of the die yield on the die area is typically given by this formula, which is an empirical formula. By empirical, I mean really a formula which fits nicely the experimental results that one has from a given plant. And it's pretty interesting, because the alpha, which is the exponent of this empirical formula, is in practice very high. It's close to 3. So that you have an exponent close to 3, to minus 3, to 3 at the denominator of the die area, which means that the yield goes down very rapidly as you increase the area of the chip. Just to make an example, if you use this formula, which fits quite well with experiments, and you assume that you have a yield, a number of defects per unit area of 1 defects per centimeter squared, okay, then it means that if then this is the curve that you have, the yield as a function of the area of the chip in square centimeters. And so if you have a chip which is 2.5 centimeters squared, so a chip which is something like 2 by 1, more or less, centimeters, which is more or less the size of a large microprocessor, with this defect yield, you have defect per unit area, you have a yield of only 16%, and you can look at these numbers. If you decrease by a factor of 10 the area of the chip, then the yield increases by a lot. It rapidly goes to about 80%, and it can be, if the chip is very small, then the yield can be significantly higher. Okay, so this is, I mean, since that number is quite reasonable, okay, this actually puts a limit to the actual size of the chip that you have. It's very rare to have chips larger than 2.5 than a few centimeters squared, exactly for these reasons, because the yield becomes extremely poor rapidly, which means an increase of the cost, which is, let's say, very high. Okay. At the moment, the larger die areas are for, let's say, FPGAs and GPUs. Those are the larger ones, because I mean, you can spend more for those type of chips. But for all, and they are at most something like 2 by 2. It's very, I mean, very rare to see something larger than 2 by 2 centimeters. Okay, so from a practical point of view, the yield problem is putting a limit on the size of an integrated circuit made with, let's say, silicon technology. Okay. Now, okay. I suggest to make a break now. Let's make a 10-minute break and then we change.